yeah, I'm with Gordon's group at the University of Passau, a PhD student there, and I'm currently working on automated program repair for Scratch. And I'd like to share some of my results with you, some of the insights. Still work in progress, so I would be very happy to discuss a few open challenges after the talk. And yeah, really curious to see and to hear your inputs. I think most of you probably know a thing or two about program repair, so I think that needs no introduction. I'm not familiar, I don't know how familiar you are with Scratch, though. I know that the Passau people are, and that's why I would like to start the presentation by talking about Scratch for a moment. So Scratch is a programming environment for young learners. So it's targeted at children at schools, but it's also used in universities to teach introductory programming courses. And it's really pretty much the most popular programming environment when it comes to this. I think 90 million registered users probably speak for themselves. And the special thing about Scratch is you don't compose your programs in a text-based fashion, writing code, you do it visually. So you can run Scratch in your browser. It will display a set of building blocks, basic building blocks for your program, and you can drag those building blocks around, snap them together, and this is how you assemble the program. And the nice thing about this approach is it completely prevents syntax errors. I mean, missing semicolons, really frustrating for beginners. And I think a picture says more than 1,000 words, so let me just show you what Scratch looks like by a picture. So what you see is the Scratch IDE, the browser window. On the left-hand side of the screen, there's a toolbox that contains your program building blocks. In the center of the screen, you can assemble those blocks and build your program. And the right-hand side of the screen contains a preview of the program. And in this case, we implemented a little game. It's the fruit catching game, a really popular game in Scratch. And the task is to catch the fruit falling down from the top. And you can move around the bowl. You can move it to the left, move it to the right by pressing the arrow keys. And you just try to catch the fruit and try to get a high score. That's the idea of the fruit catching game. And we will be using this game as a running example throughout the presentation, right? And I don't know if you noticed this, but this program actually contains a bug right here. This is the code that controls the bowl movement. And if the right arrow key is pressed, it should move to the right by 10 steps. If the left arrow key is pressed, it should move to the left by 10 steps. But here, the wrong key was selected. And so as a result, the bowl wouldn't move at all in this case. So it's clear that even though it's impossible to make syntax errors, there are still countless of ways to make semantic mistakes. You can still introduce arbitrary bugs in your code. And yeah, that's very frustrating. We've all been there, but it's particularly frustrating for young learners because they don't have that much experience with programming and they need particular care and attention and support if things don't go as planned. And that's easier said than done, though. If you think about the student density in today's classrooms and the little number of teachers who are actually qualified to teach programming, it gets a very challenging task. And so it would be nice to have an automatic solution that provides hints to young learners in the form of automatic repairs. And yeah, that's really the entire motivation why you would want to repair Scratch programs automatically. And this is where our paths converge and where program repair and genetic programming comes into play. Yeah, I think I have to mention GenProg because it's the first paper of that kind that tried to repair programs automatically. And my approach was heavily inspired by the GenProg approach. Probably everybody knows about GenProg, but nevertheless, the idea of the gist is to use genetic programming to start with an initial program variant and modify this program in certain ways in hopes of fixing the bug. And a crucial aspect is that the search is guided by a test suite. So the test suite encodes the expected behavior of the program. So this means we use the test suite to determine which parts of the program still don't work, so which parts are buggy, but we also use the test suite to encode the behavior of the program that must be retained, right? So not introduce any regression, in order not to introduce any regressions in the program when we attempt to repair it. I'd like to talk about the algorithm real quick. I made minor adaptations of the algorithm here, so I think it's worth talking about it. It uses all the basic ingredients of a genetic algorithm. So we start by inputting the program that shall be repaired and the test suite. And yeah, the algorithm, because it's a genetic algorithm, it also requires a population size. And hopefully the output will be the repaired program P prime. I called my algorithm GenProg because it's inspired by GenProg. And usually every algorithm starts by generating the initial population. And this is also what I do. And usually the literature tells you to generate this population completely randomly, which is a challenge in the context of program repair, because how do you generate programs completely randomly, arbitrary programs? And I think that's very difficult. And so instead of generating random programs, I start by generating random versions, random mutants of my original program. So there's not completely random programs in my initial population. It solely consists of small variations of the original program. And I also put the original program in the initial population once. We then start or continue by evaluating the fitness of the initial population. And this is done by running the test suite T against every program in the population. And this gives us a set of test execution traces.
Sebastian,
yeah.
can I ask a question?
Sure.
What does a test case look like in the case of Scratch programs?
Very good question. Can I postpone that question for a little bit?
Okay, so you're going to talk about this later, yeah?
I'll talk about that later, but you can just think of a test case as, you know, unit testing frameworks. For example, Jest for JavaScript or JUnit for Java.
Yeah, JUnit.
A test case for Scratch looks rather similar to that. But I'm happy to show you this at a later stage.
Okay, perfect. Okay, cool. Thank you.
Yeah, welcome. Yeah, so we get a set of test execution traces, and these traces encode which test failed, which tests passed, and in case the tests failed, what was the assertion error, what was the expected value, what was the actual value. And we can use these traces to compute a fitness for each program variant. I shall talk about this also in more detail in a couple of minutes, but for now we can just think of the fitness as trying to maximize the number of passing tests or equivalently minimizing the number of failing tests. In the end, our program should pass all tests and no tests should fail. And then we enter the main evolutionary loop. So we just keep iterating while the stopping condition is not reached. And GenProc does a special thing here because it has this additional pre-processing step where it filters the current population and it removes all programs from the population that are not viable, as they call it. So those are program variants that do not compile at all, or program variants that cannot be run, program variants where the test execution had some expected error, and these variants will generally have a fitness of 0. So we just keep those chromosomes, those programs that pass at least one test. This is then followed by the parent selection phase. So here we select couples of chromosomes for reproduction. I think that's rather straightforward. We can use rank-based selection, tournament selection, random selection. So there are different ways of doing it. One special thing, though, is GenProc only selects n divided by 2 many parents, and in the subsequent crossover phase puts back parents and the generated offspring in the population. So I think that's rather unusual or special. So usually usually I only know this, that you only put the offspring back in the offspring population. Here we also put the parents back.
Yes. Sebastian, is that different from what the original program algorithm does?
That's also what the original GenProc version does. And I think there's a discussion to be had if it makes sense to do it this way. I'm not sure of the implications of that, but maybe you can provide some thoughts on that later.
Okay.
And after crossover, we mutate every member in the population. So we apply small changes to the program. Afterwards, we evaluate the fitness of the offspring population again, and the offspring population becomes the new population for the next generation. And in the end, we can hopefully return a program P prime with no bugs, with all bugs fixed. And yeah, that would be the hope, the wish. Right, so this is how the algorithm works on a high level, but the algorithm isn't complete without also defining what the genetic encoding looks like, what mutation crossover, and what the fitness function look like. So let's dive into that right now. And for the genetic encoding, I did the most straightforward thing. I looked at the Scratch program in the browser, downloaded it to my PC. A Scratch program is essentially a zip file with a different file extension. So I extracted it, and it contains various things. So most notably assets, pictures, and sounds the program uses, but also this thing. It's a JSON file that contains the AST, the abstract syntax tree of the program. And I just take this AST-based representation and I modify the AST directly. So speaking of modifying the AST, I think it's worth mentioning the two kinds of blocks in Scratch. So on the one hand, you have statements which model control flow. Example blocks are displayed on the right-hand side. These blocks are stackable, so we can all snap them together like this, and they're in a parent-next relation. So every block has a successor, but also a predecessor. And it's very similar to a doubly linked list. And I find looking at the visual representation of the program in Scratch to be rather similar to the AST itself. And for this reason, I'll use this program representation instead of the AST-based representation throughout the presentation. And the different kind of blocks are expressions, and these generally represent computations. And the big difference to statements is they're not stackable. So there is no parent-next relationship, but if the expression takes inputs, you can nest them like this. And of course, statements ultimately can also take expressions as input, and this is how you build your programs. So how do we create new program variants then? Well, this is done by mutation. And I came up with 3 different kinds of mutations. So one being inserting new blocks, the other one deleting blocks, right? So if you can insert block, there should be a way of undoing that thing. And a third category, which is called change. So somehow modifying a block that doesn't involve deletion or insertion. But let's talk about insertion first. So let's say we have this program, a very small program consisting of 3 blocks. How could I mutate this program? And well, one way would be to just copy the statements of the program, copy what's already there. And that's one very crucial idea of GenProg. We assume that the fix for our bug is already present somewhere in the program. We just need to find it and copy that fix to the right location, right? And so one way of fixing a bug would be deleting the bug and inserting the bug fix in the right position. Another way of inserting blocks would be by wrapping them. So this orange block is called a C block, and it can wrap other stackable blocks around it. So in this case, the C block represents a while loop with a condition. And yeah, those are the 2 ways we can insert blocks. Speaking of deletion, well, okay, so I just wrapped a stack of blocks, so there should be a way of unwrapping this again. I inserted a block, so it should be possible to delete blocks. In this case, I deleted the yellow head block when flag clicked. And I could do something I haven't considered yet, which is taking a look at this expression, the touching edge Boolean, and deleting this expression. So now the C block doesn't have a condition anymore, which essentially turns it into a forever loop, but I can insert other expressions in its place in a later mutation. And the third category is changing the block in some way. So this means the number of blocks in my program stays the same, but some other things about it change. So for example, I could take these 2 statements and just swap them around. So now I'm saying hello for 2 seconds and then moving the sprite around on the screen. I could also take a look at these 2 expressions and swap those out. So now I'm moving 2 steps and I'm saying hello for 10 seconds. And I could do something completely different. For example, again, take a look at this condition. It has a drop-down menu. And I could switch to a different value in this drop-down menu. So instead of repeating until the figure touches the edges of the screen, I now repeat until the mouse pointer is touched. And I actually implemented many more different mutation operators, but you can all group them into these three categories: change, delete, and insert. However, you will notice there are many more operators that change things, and there are more operators that delete things than insert things. So usually you select every operator with the same probability. And when more operators exist that delete things than operators that insert things, you will end up with an empty program eventually, or the chances of that happening are rather high. So instead, I use something called stratified sampling, which means I choose every mutation category with the same probability. So change, delete, and insert with probability 1/3. And within each category, I select every operator with the same probability. So in the case of change, every operator, every of the 7 operators is chosen with the same probability, and so on. So if you create a stacked bar plot, it should look something like this. So every operator is chosen with the same frequency, and within every bar, the distances are the same as well, or the frequencies are the same as well. The second operator of a genetic algorithm is crossover. And the general idea of crossover is to recombine the genetic material of 2 chromosomes. And usually this is a much, much bigger change than mutation. Mutation is considered to be a small change, and crossover is a big change. So I have 2 projects here, one on the left side, one on the right side. And well, okay, crossover is usually hard to define. Mutations are usually more easy, but in this case, I could, for example, just take a look at these 2 scripts and exchange them, swap them between the 2 projects, which leads us to these program variants. So I'm basically just trying to match scripts between 2 projects and try to exchange them by copying their entire code from one project to the other. And this is what my crossover operator does. So I talked about the fitness function earlier, and our goal here is to maximize the number of passing tests. So meaning minimize the number of failing tests and thereby fixing all the bugs in the program. However, there are some challenges here, in particular when it comes to Scratch. So for example, the test suites for Scratch programs usually tend to be rather small because Scratch projects are rather small. I mean, those are programs written by beginners, and beginners typically tend to write less code or build smaller programs than experienced programmers. And small test suites are a big challenge because they induce flat fitness landscapes, so which provides little guidance to the search. I tried to illustrate this with a picture on the right-hand side. So this is a graph. F is a flat fitness function or flat fitness landscape, and G would be a good fitness landscape. And the flat fitness landscape means that we have lots and lots of plateaus. Like for project variant A, B, C, and D, there's a plateau, and all of a sudden there's a big jump to fitness of 2 for project E. So if we're somewhere around B or C and we modify the project, we arrive at A or D, but it still has the same fitness, so we don't really know if this change was good or bad. So there's very little guidance for its search, and yeah, no way to judge if we actually came closer to our goal of making a test pass. So what I much rather would like to have is the red fitness function or the red fitness landscape, where one change in a program also causes a change in the fitness value. And if I'm around B or C, I immediately know if I'm going in the right direction or not. So if I'm going down to A, I decrease my fitness, so it was a bad change. And if I go from B to C, the fitness increases, and it was a good change. I tried to reshape the fitness landscape in that way by implementing something called assertion distance. I think most of you will have heard about branch distance before. So a concept from search-based test generation, for example, where you try to judge how close a condition is to evaluating to true or false. So usually you apply this as a metric to the program under test to guide the search for test generation. But you can also apply this to the test cases themselves and the assertions in the test case. So for example, let's say we have a test that checks if the game over message is displayed after 20 seconds and not before 20 seconds. It could be a condition such as this one. If time elapsed is smaller than 20, then fail, right? And we have to make the test pass by essentially waiting long enough. But the search doesn't know if waiting long enough is good or bad, because the condition will either be true or false. So waiting 5 seconds or 10 seconds or 15 seconds, there's really no feedback there. And branch distance mitigates this to an extent. And it tells us, okay, if you wait 15 seconds or 17 seconds, you come closer to making this condition false, for example. So in this case, the assertion distance for 17 would be 3, for 18 it would be 2, for 19 it's 1, and so on. And you can see, okay, the distance gets smaller and smaller the longer we wait, and this is a way of making the search aware of the fact that waiting long enough is good. And by propagating this information forward to the fitness function, the idea is to improve the fitness landscape and ultimately improve the effectiveness of the search, right? And you can apply this to arithmetic operators. You could even use it for strings. So compute the Levenshtein distance. Boolean branches, where you just evaluate if something is equal to true or false, is tricky again. I don't really have an answer for that yet, but arithmetic operators and strings are certainly possible. So I tried to define a new fitness function that uses assertion distance and for better guidance. So remember, before, our fitness function just counted the total number of passed tests. Now I would like to incorporate branch distance or assertion distance and make my fitness function more accurate. So one way of doing that would be by taking all the failed tests F and just summing up the branch distances for those failed tests. Actually, BD stands for branch distance, but it's the normalized branch distance between 0 and 1, right? Because whenever we increase the number of passing tests, the fitness increases by 1. Branch distance values can range from minus negative integer to positive integer, and so we have to somehow scale that down to the interval 0, 1. So it's actually the normalized branch distance here. A branch distance of 0 means that our goal has been covered or our assertion succeeded. And an assertion that succeeds means, okay, the test passes. So the fitness should increase by 1. And that's why we actually have to subtract the branch distance from 1, because the branch distance decreases, but we come closer and closer to making the test pass. And once the test passes, we should have a fitness of 1. There's still a problem, though. And I'm not sure if you can spot the problem or not, but
it's redundant.
Pardon?
It's redundant. I mean, if you minimize all the branch distances of all test cases, you don't need total best. You just want to minimize the branch distance of all.
Yeah. I never thought about that. That might be true. Total passed is not needed, but I'm actually...
The entire test case passed is 0 branch distance, 0 assertion distance to all of its assertions, right?
So I actually never thought about that. But I think it shouldn't have an impact on the search itself.
Perhaps you could normalize, for example, 0 to 1 of branch distance of each test case and sum up or something like that.
Very good point.
By the way, Sebastian, you have 15 minutes, okay?
15?
15, yeah.
Oh, okay. Yeah, I'll try to speed up a little bit then.
Right, thank you.
Right, but I heard normalizing, and that's exactly what we need to do. You still need to divide those branch distances by the total number of tests, right? Because otherwise, one test case that passes one test, but fails all other tests miserably would have a smaller fitness than a program that fails all test cases, but comes really, really close to making the assertions pass. So that's an important step, the normalization here. So I implemented all of these ideas in our testing framework for Scratch. It's called Whisker. It's also a web application. It runs in your browser, and you can upload Scratch projects to it, upload Whisker tests, and run the tests against your project. And Whisker is now also able to generate tests automatically using genetic algorithms, but also machine learning based techniques. And hopefully we can use it in the future to also repair programs. So I conducted a few experiments. I took 41 Scratch projects, variations of the fruit catching game you saw earlier. And those are all real-world projects taken from a real classroom setting. So I think it's a nice choice. And on average, those projects have 14.6 failing tests. So quite a lot actually. I wrote a test suite consisting of 28 Whisker tests. Usually you have much less tests than that. And I compared my GenProg implementation against a 1+1 AI to have some kind of a baseline. Now, unfortunately, I only was able to run 3 iterations so far because, I found bugs in my implementation. And so what do? You have to rerun it again. So quick mention about the setup. So for the genetic algorithm for GenProg, I used a population size of 24, ran it for 50 generations. I used binary tournament selection and 10% mutation rate and 70% crossover rate. I had to run this on rather potent hardware because, as we will see shortly, one of the problems is test executions take really, really long. And so I had to essentially parallelize them and use the machine that has many CPUs to achieve that. So let's take a look at some of the results. So this graph shows the fitness improvement for a 1+1 EA and for my GenProg implementations. I actually evaluated a couple of more variations of GenProg. But the important thing to note here is the 1+1 EA performs worse than all the GenProg variations. So I had another variation where I only used mutation. Yeah.
The fitness improvement is exactly what number of test cases passing now, or what do you mean by fitness improvement?
It's the number of test cases that passed for the initial variant versus the number of test cases that pass in the repaired program.
Oh,
so
okay. Number
if the
of new
fitness
test cases passing.
Yeah,
Okay, cool.
exactly.
Thanks.
So as I said, 1+1 EA makes programs worse, also makes some programs better, but the GenProg variations, they all work better than 1+1 EA. It would be nice if they worked even better than that. But they're all really similar. So I have another GenProg variation that uses headless chicken crossover. The red box is regular GenProg. I have GenProg where mutation and crossover are swapped. And the brown box is actually GenProg with my assertion distance based fitness function. And I think there's still a bug somewhere because the assertion distance really doesn't have the expected and hoped outcome. You can't really see a difference to the other variations of the program. I would even say it made it a little bit worse. Another interesting thing I realized just before the presentation is, so this is a plot that shows us the initial fitness of each project on the x-axis, and for a project with that fitness, by how much the search was able to improve that program on average. And what it shows you is if a program is totally broken initially with a fitness of 0, or if a program is almost fixed with a high fitness of 25, the search isn't able to do much anymore. The program is too broken to be fixed, that's the one case, or the program is already almost completely fixed, and the search is missing something, and it just doesn't quite get there. And the best results are achieved for those programs that are half decent, that contain some passing tests and some failing tests. And I found that rather interesting. Looking at the fitness timelines, so this is a graph that plots the number of generations on the x-axis and the fitness for each generation on the y-axis. So this is for one particular project, so not representative of the entire data set. But in this case, we actually see nice gradients in the fitness, and the fitness tends to increase steadily. For other projects, though, the plots look more like this. So the orange line is the best fitness in the current generation, and that's just a flat line on the right-hand side. So the search isn't making any progress at all, and it's just stuck. So this is another plot. It shows the number or it shows the size of the program per fitness. So what it tells you is that programs that have a small fitness tend to be small, and programs with a high fitness tend to be big. And the red line shows the averages of the sizes, and the red line always increases. So the better a program, the more blocks it generally has. I guess that makes sense because many programs are incomplete, so they are lacking code, and you fix bugs by adding code. But on the other hand, this is a plot that shows the runtimes for the test suites for each project's fitness. And this is very interesting to me because the smaller a project is, the worse its fitness is, but the longer it takes to run the test suite. And the better a program gets, the more the runtime decreases, even though the projects tend to increase in size. I think that's very fascinating, and yeah.
The bigger the program, faster it is.
It's yeah, I think it's just a nice observation, and maybe we can even use this to our advantage if by adapting the search to that, maybe. So here's another violin plot that shows the distribution of the run times. So the x-axis, the scale are milliseconds, and you see that the vast majority of projects is evaluated in under 5 minutes, and there's a big number of projects that takes just about 100 seconds to evaluate, and that's just a really long time for such small projects.
Sebastian, we only have 5 minutes, okay?
Yep. I'm almost finished. So one of the challenges I just mentioned is the high number of bugs per project. So usually you have 1 bug or 2 bugs to fix, and here it can be 14 bugs. But at the same time, our test executions take a very long time, and our test suites really aren't that big. We don't have many test cases, and that creates flat fitness landscapes that are deceiving. And another thing is, because the projects are so small and Genproc assumes the fix is already in the project itself, there's a limited scope where we can draw fixes from. And yeah, that concludes my presentation. So I don't want to waste any more time. Thank you very much for your attention. I'm happy to take your questions and comments.
Thank you, Sebastian. They're talking, I don't know if you can hear it. All right, any questions? Okay, Justina has a question.
Hi, Sebastian, thank you for the talk. I have a few questions about the decisions made. So firstly, the most striking one to me is the 70% crossover rate. That seems very high. And there have been results that show that mutation is actually more successful than high crossover rates. So why decision?
It's a standard crossover rate that's used in test generation, which is a different domain. So it probably doesn't work well in automatic program repair, but that's just what I was familiar with, so I went with that. But it's a very nice insight that crossover rates 70% appear to be too high. Definitely.
While we are at the node, maybe have you tried using local search, which is only mutation operators, right? We have to put. Did you have local search? Oh, 1 plus only A. No. GP mute. Oh, I see. So that's only mutation.
That's only mutation, yes.
Use it just much lower.
Oh, much lower. Okay.
Yeah, increase mutation rate. You also reduce the running time.
You could reduce the running time. Right. Bill has a question.
Hi, Bill has lots of questions. So what I was wondering was, when you do your crossover, when you do your mutation, you're operating on the AST, and then you generate the programs back from the AST. Is that right? Okay. The things that you generate, do they always compile? Do they always run? Or do you still get syntax errors?
The operators I designed very carefully. I haven't experienced the case where a project didn't run yet, and I created millions of Scratch projects so far, different Scratch projects.
Very good. That was exactly the answer I'd hoped for. Thank you.
Okay.
All right, any more questions? I may have an intuition about your results and why, sometimes keeps going up and down. I think your elitism is something, it's too little elitism in my opinion, and that's my opinion. For example, in an SJ2, instead of adding, the offspring and some parents, they add everything to the new population and filter out, by ranking them. So if you did some sort of hard elitism like this, there is no way your function would be going down. So it would always go up or plateau.
By the way, just a comment on that. That's why also in GenProc they add parents. That's why you ask why in GenProc they kept parents. That's the reason, basically.
Really, but still, that elitism is a little bit too weak. I think you can make it a little bit stronger. Join both populations of offspring and parents, and then rank them by their fitness, and only select the N best, regardless of whether they're parents or offspring, for example.
Yeah, I absolutely agree. I have this implementation ready, and I also ran it, but unfortunately there was a bug in my elitism. But I'm on it. It'll be fixed soon.
So you come into your implementation. Is it open source? Is it planned to be released? Can you give an intuition about how difficult it would be to extend or work with your existing implementation?
So far, the implementation is in a private branch of our Whisker repository. But once the results are reasonably good enough, we'll push those to our public GitHub repository, and then it's available for everyone, probably when the paper has been released about it. And so the architecture is inspired by EvoSuite. So I don't know how easy it is to extend EvoSuite's implementation. I found it's
very
easy enough.
It's best generation tool for test cases.
Yeah, I have to say that when Gordon is here.
Another question, maybe I missed that. How do you do fault localization?
Fault localization is done by spectrum based. So I use OCI currently, but the problem with that again is fault localization doesn't really work because
follow-up thing. No, though, I assume, because you mentioned large runtime of tests, have you checked the coverage? As in, does it only cover the methods, or that only touch the buggy code, so you can use subset of tests, so that you don't waste resources?
So I haven't checked the coverage actually, but it achieves full coverage on the fixed variant, and the buggy variants are generally just missing code. So I would assume that pretty much everything is executed in the buggy programs as well. But the biggest problem about fault localization is the small number of test cases. So usually like half of the entire project is buggy according to fault localization. So you don't really know exactly where your mutations operators should be applied to. And yeah, that's one big problem.
Okay.
I can go on.
Okay, there you go. Sorry.
On the mutation operator front, you mentioned you did the stratified sampling. One other thing that we've tried in the past to work better, because if you think of deletion, the deletion space is much smaller than copy or replace, because deletion is n number of statements, then copy replaces n squared. So obviously, if you do just equal sampling, then delete will be biased towards delete. There's no doubt about it. So what about trying to, calculate the space for each, just taking into account locations into account, and then biasing that. Another thing that we've tried is just reinforcement learning during search. In terms of saying which mutation operators and locations are promise, should promise, shall we say. So that's that. And there are a few references I'll send you later.
That would be great. Yeah, thank you very much.
Hi, Sebastian. It's Federica here. Thanks for the talk.
Hi.
Just a comment/question regarding the fact that you said you have few fixed ingredients available in a given program. I was wondering first if it's feasible with this type of program to grab the fixed ingredients from other programs.
Yeah.
And if you do this, probably this could then put the crossover, because it looks like that the offspring you have created is weaker than the parents, and this could be due to the actual lack of fixed ingredients. So that could be a way to, if you keep the crossover with that rate, could be a way to improve.
Definitely. And we're in the lucky situation that we have 41 different project variants.
Yeah, you have a lot of projects, so that you can use all the rest as code base, right? You have one target and all the rest will be code base. We did this with Java programs, and it didn't help massively, but it helped.
It might help. It might help in the context of Scratch when the programs are like really broken and if programs don't contain much code at all. Yeah, so I'll definitely try that. Thank you.
You also have an adaptive version where you analyze the program first. And if that's the case, you decide to use external code base, external to the project.
The population is very small.
Oh, yeah. That's a good point. Another point I want to mention, we had 50 generations and 24 population size. It seems to work better to have a larger population with fewer generations. The other way around. Anyway, just an empirical, there's no theory behind it, just from experience we've done. Yeah.
Okay, I'll try.
The last point probably also compare with random generation, because especially in the cases where you have that always max fitness function, probably if you just generate randomly a larger, like the same number of solutions that you evaluate, you'll get the same results. So
I
have that benchmark just random.
Just prove that there's something going on.
Yeah.
So how do I do random search with program repair though?
No, you can simulate it just generating the first generation, not evolving. You just generate 25 by 40. You do the same number of fitness evaluation you do in total. I don't know, let's say you do 250 in total. You just generate 250 solutions and evaluate their fitness without doing any crossover mutation. It's just one generation created and evaluated. The first generation.
Okay.
You can simulate it that way. No evolution, basically.
Okay. Yeah,
it's a sanity check for you. So you have that always available, a sanity check to see if you all these changes that you're gonna try, all the different design choices, if they actually make a good difference to that.
Yeah, I think that makes a lot of sense. I will definitely do that. Yeah, thank you.
All right, any more questions? Yes, we. Oh yeah, you didn't show a test case to us again. We showed,
that's true.
I mean, what does it look like? I mean, you showed that. Yeah, you showed that.
Yeah, sure.
And how did you create the test cases for the analysis? Did you do it automatically, or did you do it manually? Because I've read a paper in SSPSC 2020, very good one as well, about automatic generation of test cases for Scratch program.
Yeah.
Yeah.
So this is what those test cases look like. It's JavaScript code, and it's basically similar to any other unit testing framework. So there's a way of controlling parts of your Scratch program. For example, I can move the bowl around manually if I want to. I can send different inputs. I can wait for some time. I can read properties of variables, and I can have assertions. And this is a test suite that was written manually. We can generate tests automatically.
Sorry, Sebastian, I think I missed a bit. So are you using JavaScript as a player of the Scratch game? Is that the idea?
Yeah. So the JavaScript code controls the inputs of the bowl and the inputs of the program and the test.
Oh wow! Okay, so that you need to be really a very good JavaScript programmer to be able to do that.
To be fair, other people already worked on that before me, and it's probably their work. But you're right, JavaScript is not that pleasant to work with sometimes.
Oh, okay. But so I guess another question was from the back was going to be, how do you generate these automatically, or are they all manually generated?
So for my evaluation, I used manually written ones. For automatically generated ones, I would just use Whisker, clicking the test automation button here and start test generation.
Okay, thank you.
Yeah, one other comment that even in the APR community, like state-of-the-art, fixing multiple bugs within one software is very challenging. So just want to say it's not surprising that you might struggle there. They're really good at single bugs rather than multitude. So it's still a bit of an open research problem how to be able to do that. Yeah, that's it from me, I guess.
Okay, thank you for putting that into perspective.
Yeah.
All right. Any other question? I think we're kind of over time. Well, thank you, Sebastian, for presenting to us very interesting work. I hope you managed to improve it, and hope to see a paper about it soon.
Yeah, thank you very much for having me. It was a great pleasure to talk to you, and yeah, looking forward to hearing from you again.
All right. Well, thanks, everyone. All right. Thank you, Sebastian. Bye. Thank you, Gordon. Bye, everyone.
Bye.
Bye.